Morning. Guess everybody's tired. Let me wait for 2 minutes.
While we're waiting, can I ask you a question about the project?
Yeah.
A lot of the parts of the project have a little sentence, why is this happening? What do you think's happening? How would you like us, do you want a report or something with all the figures in it and comments?
No, just a brief explanation of, okay, I know physically this is why this should happen. This is what I see. That's it.
Okay, so like a Word document with the figures and then like
Yeah.
a sentence under it?
Yeah.
Okay, cool.
Okay, I guess we can start and people will trickle in slowly. So if you remember last time we were talking about Rungakuta 2, and this is the example that I made up from my head. If you just use slightly different numbers, you will get much better results. So these numbers are actually match the parabola that we were working with previous to this. Okay. So that's just an aside. And again, there's nothing wrong with the process that we went through. All right. So, do you have any questions about the project? Project is due in 1 week. Oh, you already asked me a question. So sometimes the questions say explain what you're seeing. So just write a few sentences, 2 or 3 sentences, explaining physically why what you're seeing in your simulation makes sense. Any other questions about project? I actually want to show you what your results should look like. So I did a quick I wrote a quick code for convergence, and it's basically going to solve the heat equation for different sizes of grids. So this was on a very coarse grid, and the analytical answer, the exact answer is the circles, and your numerical answer, starting from the initial conditions, should slowly converge to the analytical answer. And that's very typical of what diffusion looks like, right? If there was no forcing term, this peak would eventually diffuse out to 0. But it diffuses out to this sinusoidal curve because you're forcing. It's a non-homogeneous solution. Okay. And so that's for the first problem. You should get something similar. And then the third problem, where you don't have 0 boundary conditions, but you're actually taking one end of the rod and you're increasing temperature and decreasing it again sinusoidally. This is similar to what you should do. Okay, now I will close that. Okay. Oh, one thing I forgot to mention last time was when you're optimizing your code, what are you shooting for? What is your goal? Your goal is to write blazing fast code right from the get-go, right? No, no. Your first priority is always to write correct code. I have worked with many, many people who, are fascinated by the computer science aspect and they start very low-level optimization very, very early on, and then it becomes very difficult to debug what might be wrong if there's a bug in the code. So always write correct code and then you write fast code. Okay? But simple things like loop ordering you can already ingrain in your brain because it's always a good practice. And MATLAB actually has a profiler built in, which I forgot to show you the last time. I can show it to you now. I'm sure Python has something similar. So let me go here, back to MATLAB, and so if you just go to home and go to where run and time. So this run and time will open up this profiler. And then when you want to profile your code, you go to editor and then again hit run and time. And now the profiler is running 3 seconds, 4 seconds. When the code finishes, we will see the output. Okay, I wish I'd done this faster. Okay, let's let it run. Okay, so once the code finishes, you get a profile of the timing for each of the function calls. So if you go into project 1, these are the various things that project 1 is doing, the project 1 code. And you see 90% of the times is spent because I put a pause in there so we can see the graph. And then you can use this information to identify bottlenecks and figure out where you should focus your code optimization effort. Okay, so all right, that's about provider. Any questions? Okay, so today we will look at classification of PDEs. There's 3 main classes of PDEs that tell you what the behavior of the solution will look like. So you've probably heard of this before. It's parabolic, hyperbolic, and elliptic. Okay? And the way this classification is done is for the second order PDEs. So classification of PDEs that are second order. What that means is if you have something like A by xx plus B by xy, C by yy, and then you also have low order derivatives. Okay, so what matters here are the high order derivatives. And so we say that this PDE is hyperbolic if b squared minus 4ac is greater than 0. And if this basically looks like the solution of the quadratic equation. And it's called parabolic if this is equal to 0. And it's called elliptic if this is less than 0. So have you seen this before, this sort of classification? Yeah, right. So now do you know how this relates to how the solution behaves? Have you heard of something called characteristic lines? No. All right, okay. So some of you have, some of you haven't. So these properties are related to how the characteristic lines behave. So the characteristic lines, and I will explain what exactly they mean. So the very first thing that we can say is hyperbolic equations have two real characteristics. Okay, and parabolic equations have one real characteristic line. And elliptical PDEs have no real characteristics. All right, and in a few moments I will tell you what exactly is a characteristic. But first, let's look at some examples of these three types. So hyperbolic, if you have heard of the wave equation. Okay, it's basically phi dt equals c squared by xx. I forgot to mention, when I have these subscripts, it just means the derivative. Del t squared. Okay. All right. So let's see. We just rearrange this with phi dt minus c squared phi xx equals 0. Okay. How do we know if it's parabolic, hyperbolic, or elliptic?
Plug it into the b squared minus 4ac.
Yeah. Plug it. We just need to figure out if this is positive or negative, okay, or 0. Now, don't be confused by this xx and xy. These are variables. They can be whatever. So right now we're dealing with x and time. So we have xx and tt. So we have a and c. All right. So here, our a is equal to 1, and okay, small c. Capital C is equal to minus c squared, and b is 0, right? Which means b squared minus 4ac is basically 4c squared, which is greater than 0. So hyperbolic. Okay, now this is the 1D wave equation. What about the advection equation? That's the one we've been talking about. 1D advection equation. So if we have del phi by del t equal plus c del phi by del x equals 0. And now this c is basically our velocity. So I've replaced u that we've been using with c, wave velocity. What is the order of this one?
First order.
All right, it's first order. And can you tell me what its behavior will be? Will it be elliptic, parabolic, or hyperbolic?
Parabolic.
Because?
There's no second order terms.
All right, so you're saying it's parabolic because A, B, C are all 0, right? Yeah, that's what, the first time I saw this, I said, yeah, parabolic. But it turns out that it actually behaves like a hyperbolic equation. And remember that this classification is valid for second order equations. When you have purely first order PD, this does not necessarily apply. So this actually behaves, so we would say this does not how should we say? This does not follow the classification scheme, since it is a first order PDE. But it actually behaves. Behavior is hyperbolic. And today I will show you actually a solution of this advection equation, and we will see how it behaves as a parabolic equation. Okay. All right. So we've looked at the hyperbolic example. There's two more left. Let's bring back the. Oh, can I remove this? Let's bring back the heat equation. We had del T by del T equal kappa del 2T over del x squared. So can you tell me what is this? Hyperbolic, elliptical, parabolic. Sorry, this is x and x. It depends. Did you say it depends? No. Okay. This one is not tricky. The one the wave equation was the one the advection equation was tricky. So this is
Hyperbolic.
This is hyperbolic because
Plug it into b squared minus 4ac.
okay,
There's
what?
no b or c.
So b squared is 0, 0. A and c are 0.
Negative kappa and 0.
All right.
Oh, and 0, so.
Yeah, so it's parabolic, right? So here our A is minus kappa, B is 0, and C is 0. Yeah. There's no second derivative in time, so right. So which means b squared minus 4ac equals 0, so it's parabolic. That's the 1D heat equation. Okay. So now we have an example for elliptic, parabolic, and the last one is, no, we have an example for hyperbolic, parabolic, and if you look at the 2D Poisson's equation, we get, let's take pressure, okay, del 2 pressure over del x squared equal f of x, and there's a y also. So it's the 2D Poisson's equation of x and y. Okay, if we just rewrite this as a, so this exx plus eyy equal f. Here we have a equal 1, b equals 0, c equal 1, which means b squared minus 4ac is less than 0. Okay, so fine. I mean, these are mathematical classifications, but what does it really mean physically? If you've ever worked with the pressure Poisson's equation, you know that any change you make in the field in the flow domain at any point, what happens? If you've worked with it, you might know. So do you know what happens? So if I have, let's say, a water tank and I perturb it, I drop a ball at one corner, what happens? Physically, what happens? No, come on, drop. So okay, you have a tank of water, okay, and you drop a huge object at one end. What will happen?
Ripples.
Yeah, you get ripples, right? You get these waves propagating out. And they actually follow the wave equation, which we've seen is hyperbolic. So most PDEs that behave as a hyperbolic PDE have this sort of wave-like solution, where the information propagates out in all directions. Okay. But if you think about the pressure, what happens to the pressure? Does it also come in waves? If you're not, okay, so this was a surface, right? Now, if we have a completely submerged aquarium, right? There's no surface. So let's say it's a closed box and there is it's a fish tank and there's some toy here and this toy keeps vibrating left and right. Okay? What happens to the pressure inside the tank? If you're measuring pressure at this corner, what will you see?
Keeps fluctuating.
It will keep fluctuating. But how do you think it will behave? So here, if I'm over here and I'm trying to measure the surface wave, I have to wait until the wave reaches me. If you have a pressure sensor here, do you have an idea of how much time will elapse before you see this change in pressure?
Speed of sound divided by distance.
Speed of sound, yeah, so that is correct. The information will propagate out with the speed of sound, but for incompressible flow, if we make the incompressible assumption, the speed of sound is, it's what?
The change will be instantaneous.
Change will be instantaneous because the speed of sound is infinite. So, in incompressible flow, the change in pressure that you measure will be instantaneous. And that's what elliptical PDEs, that's how elliptical PDEs behave. Okay? Any change you make at any point in space or in time propagates out to all other points instantaneously. There's no delay. Hyperbolic PDEs, there is a delay. So if you're over here and you are wearing a blindfold, you will not know that these waves are coming until they hit you. So you have to wait to feel the disturbance. Okay, make sense? Parabolic PDEs are somewhere in between. So the change does happen with infinite speed, but it's not as abrupt as in the case of elliptic PDEs. Think of the heat equation. If you have a profile, it diffuses out slowly. Right? So that's parabolic behavior. So that's what we saw here. Heat equation is parabolic. Okay. So what are these characteristics that I was talking about? That's the two things I mentioned, right? Depending on the class of the PDE, the characteristics behave differently. And there you have either 2 real characteristics, 1 real characteristics, or 0 real characteristics. Okay. So what are these characteristics? So characteristic lines are actually the path along which the solution propagates. Okay. Before we go into detail over there, let's take a look at again the advection equation. Del phi by del t plus c del phi by del x equals 0. So this equation actually has an analytical solution. Okay. So the analytical solution is if you want phi at any x comma t, that's the solution of the PDE, you basically look at the initial condition and what happened to it at x minus ct. Intuitively, this is just saying that whatever profile I start with will just keep getting advected without any change to the shape. The way it looks at the current time, let's say that the way the solution looks at time equals 2 seconds is what it looked at time equals 0 seconds, but just moved, okay, with speed c. Make sense? Okay. So let's see if that's actually true. I will show you the solution for the advection equation, an upwind solution. Okay, so the advection equation here, put it up. Let's see. Let me pick order 1, passive scalar, yes. Okay. Okay. So if you remember, we were talking about upwind schemes. That's exactly what I coded up in here. So this is what the solution looks like. If I start with a Gaussian profile, slowly it will get advected in time. Okay. There's too many of them, so let me simulate it for a smaller time. Let me simulate it for 0.2 seconds. Okay, so that's exactly what's happening. The profile, initial profile is shown in blue, and it slowly gets advected with this constant velocity that I've specified. I specified that the velocity should be where is it? Here. The velocity is 1. Okay. All right. So what's happening? Does this make sense? Something is wrong?
The peak is getting.
The peak is getting smaller. And we just said the whole shape should advect with no change, right? So something is wrong. What is wrong? Did I make a mistake? Did I put in a bug? What could be wrong intuitively? this looks like diffusion, right? I wrote the code for pure advection, but there's something that looks like diffusion. So if you remember, whenever we discretize our derivatives, what are we doing? We're making an error. Do you remember where the error comes from? Where?
Numerical errors.
Yeah?
The round of error.
Okay, there's round of error and there's
The
the
error from the Taylor series.
yeah, the error from the Taylor series, which is the truncation error. Okay, so that truncation error is actually what's causing this bad behavior. And today we will see exactly how we can pinpoint that. Okay, so that's a first order scheme. What can I do to improve the behavior? I can use a second order scheme for adventure, right? Let's see. Okay, that's better already. So the first order scheme has this huge error, this huge diffusive error, which my second order scheme does not have. Eventually, this will also start showing bad behavior if I let it run for long enough. So let's run it for, let's say 5 seconds, and let's plot it every half a second. Okay, let's see. Okay, so now you see, okay, maybe that's not clear. Let's plot it every 1 second. Okay, so this is basically the whole thing making 5 rotations, and I'm only plotting every time it completes a full rotation. What is wrong now? So you again see this peak is decreasing, but much slower than it was for our first order case. If this is full 5 rotations, I'll redo it with the first order case. But now there's also something that's happening over here. If you think about this being scalar concentration, for instance, a blob of ink being just advected with no diffusion, what does these negative numbers represent? Like saying I have negative mass. This is a terrible thing to have in a simulation. So there's many ways that you can fix these errors, and we will look at some later on. Okay. So okay, my higher order scheme behaves slightly better, but it's still not perfect. Let me just rerun this with the first order for these 5 rotations, and let's see what happens. Order 1. Okay, so it does not show these strange negative numbers, but the diffusion is huge. Okay, we've gone from 1 to almost 0.28. So these are, again, numerical properties. This is related to something called Gordon-House theorem, where first order schemes will not give you oscillations, these spurious oscillations that we saw in the second order scheme. But the first order scheme has huge diffusion. Also with the second order scheme, what we were seeing was the shape gets distorted. So this is called dispersive errors. And all of this is related to how the truncation error behaves. Diffusive errors and dispersive errors. So we can actually, let me skip forward and we can take a look at these errors since it's fresh in our. Okay, so so now what we can do is we can try to relate diffusive and dispersive errors in our numerical solution to the truncation error. Okay, and do you remember how I said what is one of the best ways to discretize this advection equation? Upwinding, right? So what should I write for the derivative, time derivative? Tell me.
Phi I n plus 1
Phi I n plus 1
minus phi I by delta n by delta t
plus
plus c I
okay,
phi I minus 1 n for u greater than 0.
so let's assume Ci is greater than 0, right? And then this
I
should,
minus 1, sorry, I minus phi n I minus 1.
yeah, so this is a first order discretization. This is actually exactly what I coded in the first order result that I was showing you. Okay, so let's see, where does this diffusion term arise? This very large diffusion term from this discretization. Okay, so if we just take the Taylor series expansion of phi I n plus 1, what does this give me? It's phi I at n plus delta t phi dot plus delta t squared factorial phi double dot plus blah blah blah. And now phi dot is time derivative and phi prime will be space derivative. Okay, similarly we can write phi at n I minus 1 is phi I n. Stop me if I make a mistake. Yeah. Alright, so we have the Taylor series expansion for the next time step phi and the previous grid point phi. Okay? What we can do is we can just plug these into our discretized equation. So let's call this A. Let's okay, so when we plug these examples into A, what we get is, let's see, phi I n plus 1 minus phi I n. So this minus that divided by delta t is just phi dot plus delta t over 2 factorial phi double dot phi triple dot and higher order terms. Okay, so that's just this bracket becomes this bracket. Okay, and the next term is, okay, let's see, phi I n minus phi I minus 1. Okay, so it's basically this minus that, negative of that. So we have, divided by delta x, we have phi prime minus delta x over 2 factorial plus higher order terms equals 0. Make sense? I've done nothing fancy. I've just taken these Taylor series expansions and plugged them into the discretized equation. So what happens now is we are starting to recover something that looks similar to what we want. We have a phi dot plus ci phi prime, and we have all these extra terms. So let me keep the first order terms. Delta t over 2 phi double dot a minus c delta x over 2 phi double prime plus higher order terms equals 0. Okay, what do we do next? What were we trying to simulate? We were trying to simulate the advection equation. But what we've ended up is we're ended up simulating this equation. Okay? So if we just rearrange this, this becomes del phi by del t plus c del phi by del x equal as the c delta x over 2 del 2 phi over del x squared minus delta t over 2 del 2 phi over del t squared plus blah blah blah. Okay? What do you see now? Do you see the source of our huge numerical diffusion over here somewhere? Where is it?
The
The
whole right hand side.
whole right-hand side does cause an error, but the very large diffusion that we saw, it looked like physically what diffusion would look like, right? And what is a diffuse? What does a diffusive term look like?
The first term.
This first term here looks very suspiciously like a diffusion term, right? That's what we have in the heat equation. On the right-hand side, we have the second derivative in space. So this is actually the source of diffusion. We can even represent this time derivative as this space derivative, okay? So let's very quickly do that and see how this changes to spatial diffusion. So for that, okay. So let's try to convert phi dt into phi xx. Okay. Let me call this whole thing alpha. Yeah, I will rewrite it. Okay. So to read it, and this is just phi t plus c phi x equal e delta x over 2 phi xx minus delta t over 2 phi dt. And let's ignore the higher order terms again, and let's call this, let's say, g. Okay. And if we do if we take the time derivative of this, we get phi dt plus c phi xt. I'm assuming the c is constant here. Phi xxt minus delta t over 2 phi e dt. Okay. And if I instead do partial with respect to x, we get phi dx plus c phi xx, c delta x over 2 phi triple x minus delta t over 2 phi dt. Okay, so how can I start relating my, what am I trying to do? I'm trying to convert my phi dt into phi xx, okay? So let's see, if I get rid of this xt and xt from here, I will basically recover a relation between tt and xx. So let me see, what should I do? I should do the first equation minus c times the second equation, which gives me by dt minus c squared by xx equal all of this, equal this higher order terms. Again, which I'm ignoring. All right, so now I have a relation for an estimate for how my phi dt can be expressed as in terms of xx. All right, so let's go back to our modified advection equation, and what we get is, so I'm just rewriting. Okay, and here we had a phi dt, so we replace that with a c squared by x and x, and there's I over. This is phi x and so what we have is c delta x over 2 times 1 minus a c delta t over delta x. I've just regrouped these two, and yeah, that's just becomes the bracket. Okay, so this basically is our. Oh, sorry. What is this term? This term on the right hand side should this be present in our advection equation? It should not be present in our pure advection equation. Pure advection equation is this equals 0. So this is something extraneous because of the numerical approximation that we have made in our discretization. Okay? So this is called, the whole term is called dissipation error. Okay? And there's something called numerical diffusivity. Numerical diffusivity. Can you tell me from what I've written what this should be equal to? Once more? Yeah? Louder.
This c times delta t minus delta t divided by delta x must be less than 0, less than 1.
You're talking about stability.
Yeah, but this depends on, this creates a dissipation, right?
The stability creates, okay, so that's actually a very nice point. You remember we were talking about what happens when CFL is exactly equal to 1. So you will see here, this term will become 0. And our advection equation becomes exact. Okay? So you can see that mathematically from here. But if we are just talking about what is an equivalent physical diffusion due to this numerical error, that's what you would call the numerical diffusivity. Okay? What's a physical diffusivity? You know it as what symbol? In heat equation, it's kappa. In fluid mechanics, it's what? Alpha? No. It's new, right? It's the diffusivity. It's the fluid viscosity. Okay. So, I will write that down. Many of you might not have seen that. So numerical diffusivity is just this constant term over here, c delta x over 2, 1 minus c delta t over delta x. Okay? And this is just saying that my numerics causes this sort of physical diffusion, which is fake. It should not be there. Okay? But now we see exactly where it comes from. And if I will play the animation once more, and we can see that it exactly behaves like a diffusion term. Okay, so a few things to note as you guys were saying. Note, if the CFL number, which is c delta t over delta x, is exactly equal to 1, we get exact advection. And you might remember that from the time we were talking about semi-Lagrangian advection, where we were saying, okay, we need to jump from this cell and trace back where we were, and then interpolate. But if we jump from one cell to the next exactly, there's no interpolation. You just move the value. Sorry, I didn't see that. So we were talking about semi-Lagrangian inflection, that where you trace back your grid node and you end up somewhere in the middle, then you have to interpolate the value here. But if you end up exactly on the other node, you just move from this node to that. Okay? And that was the exact advection. And here you can see how it all ties together very nicely mathematically with the truncation error. If we have 1 minus c delta x, but if we have the c delta x over delta t equal 1, the numerical error is 0. Numerical dissipation is 0. Other terms might also be 0. For that, you will have to include higher order terms. Does not term is 0. Does all of this make sense? So now you see how mathematically we can show what we observe in our simulation. I will play that simulation one more time. As it comes up. Wow, that didn't take me so long. Yeah, so with the first order a discretization, okay, order 1, this is exactly what we have done on paper. This is exactly the equations we have written on paper. Okay, after one full rotation, this peak goes there, there, there. And if you compute the diffusion term that we have just now derived, you will see that it will basically be the coefficient that you would implement in a physical diffusion scenario. Okay? All right. So let me see. Okay. Fine. We know there's this dissipation error, and there's also this dispersion error that I mentioned earlier. So what happens is in the truncation error, in the modified PD, odd, even ordered derivatives. These are the errors in the error term. In the error, they constitute what's called dissipative error, and that looks like diffusion, and odd order derivatives. These are what cause dispersion error. Okay. This is when dissipative is when peaks get washed out. Dispersive is when the shape basically gets distorted. And that happens because it affects the wave speed details, which we don't need to worry about for now. Okay? Everything makes sense? All right, let's see. So now we can talk about character. So first, I showed you this solution of the advection equation with the passive scalar, right? With a very nice, smooth field. What happens if I change the field to be a non-constant? So what happens if so here, if you see, my velocity is basically 1 everywhere, right? Which is what we were seeing in simulation. What if I change this to be, let's say, a Gaussian? So it's the same as the initial condition. Okay, to make sure that this makes sense, I will go here. Where's the plot? Plot. Okay, I wish I had not done that. First plot is first. Yeah, perfect. Okay. All right. So what I've done is, again, this is my initial condition, initial distribution of phi. But now I'm saying everything moves with a velocity field that looks like this curve. Okay. Physically, what will happen? Will we get the same nice advection of the profile? Something else will happen? You can do this, by tracing the profile on paper. So if I knew that this was moving with 1 meter per second to the right, I would just say, okay, after 1 second, this will have moved 1 meter, so 1 full cycle. Okay, that's too much. Let's say this is moving with 0.1 meters. So after 1 second, this peak would be at 0.6. Okay, whereas this would have moved 0.1 meter to the right. But now with this non-constant velocity, what happens? Let's think about the peak. What's the speed of the peak relative to everything else? Does this make sense or not? I can rephrase it. Do you know what I'm asking? No. Okay. So, the first problem that we saw, this was what? Phi, this is phi 0. This is the initial condition. Okay. Now I can also plot the u. So that would be x comma u. Okay, let's go back to the simple problem, which was this. Okay, so going back to the simple problem, now this is my initial scalar profile, and my initial velocity looks like this, and this velocity will not change in time. Okay. So at every x, we have this constant 1 meter per second to the right. Okay? So basically what happens is everything moves together. Now, if I do something more complicated where, again, I have the same initial profile, but I say now my u looks something like this. Okay? It's no longer a constant at 1 meter per second. What will happen? What will start happening to this profile? So let's think about a blob that's at this location. Yeah. What speed does this blob move with?
1.
It moves with this velocity, which is 1 meter per second. What speed does this blob over here move with?
0.
Almost 0 velocity. What speed does this blob move with? Almost 0 velocity. So can you see what will start happening to the profile? All of these blobs start moving to the right, nothing else is moving. So it will start forming something like a shock. Okay? And that's actually exactly what happens. So let's let this play. Okay, let's visualize more, 0.01 actually, and let's simulate for a smaller time. Okay. See, that's exactly what you were saying. The peaks start moving faster, everything else is either not moving, this region is completely not moving, this stuff is moving very slowly. So slowly you will start piling up, okay, and forming a shock. That's a very a shock is like an infinite gradient. And also because of diffusion, our total integral actually decreases. It should not, but it does because of numerical errors. So even with this very simple advection problem, you can get very complicated solutions depending on your velocity. What more can we do? We've advected our passive scalar, which does not influence the velocity. But we can also say, okay, we will advect the velocity field itself. Okay, which would look like, what would it look like? What would the equation look like? Tell me.
Dou u by dou t plus u dou u by dou x equal to 0.
All right, yeah, so it's just the advection equation, but instead of a phi, now we have u inside. This should look familiar. Where does this come from?
The material derivative.
This is the material derivative. Yes, you're right. So this is du by dt equals 0. So the left-hand side is the material derivative. But in terms of conservation laws, does this look familiar to you? What are the two most important conservation laws that we will deal with?
Mass and momentum.
Conservation of mass, conservation of momentum. Does this look like it's sort of resembles one of them? Which one?
Moment.
Momentum, all right? So, conservation of momentum is in its full three-dimensional glory is this. Okay? So, this left-hand side looks similar to what this would be in one dimension, right? So, in one dimension, in 1D, this would look like del u by del t plus u del u by del x equal minus del e by del x, and there's a 1 by rho here, plus nu del 2u by del x squared. Okay? So you're beginning to see that this full complicated Navier-Stokes equation is actually made of things that now we know how to solve. This is what we've done for the first few weeks. This is how you solve the diffusion equation, diffusion or heat equation. Okay, and today we've looked at a solution for the advection equation. But the solution we looked at was for a simple passive scalar, not for this advection of u. Okay, so I will make just one simple change in the code, and then we can look at how u behaves. Okay. So now you must be wondering why I told you about all this elliptical, hyperbolic, and parabolic. Now you can begin to see that this part of Navier-Stokes behaves as what? As what class? So each part of Navier-Stokes shows different behavior, different class behavior. All right, so what does the advection equation behave like? You have three options: elliptical, hyperbolic, parabolic. Hyperbolic. So this behaves as a hyperbolic PDE. What does the diffusion equation behave as?
Parabolic.
Parabolic. And pressure correction, which I will talk about in the next few classes, this behaves as an elliptic PDE. So now you should see how everything is connected. Everything that we've been learning is basically pieces of how to solve this equation. Okay? So let's go and change my code to advect u instead of phi. Again, I did not have to do a lot of coding for that. I just, right, you're not seeing my screen. It was basically more of a copy paste and changing one or two lines, and I can go from a passive scalar to a full active scalar. Active scalar is u. Okay? And if I run this first order now, what should happen? What should happen? Will we get a nice advection of like the one-dimensional profile? Let me pause it after the first one. Yeah. So now u itself is being advected. Okay. This is u. So water here moves faster than water here, which is stationary. What will happen?
Will it flatten out?
It flatten out would be what happens if you have diffusion. Oh, you're thinking about surface, like water is higher over here and lower.
Yeah.
No. What I'm saying is, this is like a one-dimensional tube where the velocity of the water at the center of the tube is 1 meter per second, and at the ends is basically 0. Okay? So water is a bad example because it's not compressible. Air would be a better example. Okay? What will happen? And it's a pure advection problem, no diffusion. Remember what happened when we had a scalar being advected with this u? We had a very sharp gradient. Something similar will start happening. These blobs of fluid moving with 1 meter per second will move to the right, and then the velocity of that blob will change at the next time step. Okay? Because I've said it, and then everything will start piling up. Okay, let's see if that happens. Let's move this. You see there's like a tendency to form an infinite gradient over here. And these are actually called shockwaves in fluid mechanics. So mostly you see this with aerodynamics because in water it's very difficult to produce shockwaves. But in aerodynamics this happens very, very easily. So the supersonic planes that used to fly, they had a very strong shock wave in front of them, the contour. And if you actually see visualization of a bullet, it actually traces a shock wave in front of it. We can actually do that. So, let's see. The only condition for this is that things have to be traveling faster than the speed of sound. So you have to.
My boyfriend is addicted to frozen food porn.
Hey, it's Destin, and welcome back to Smarter Every Day. As long as I've understood the physics, I wanted to visualize the shock wave on the front of a super.
Okay.
It's a big boom, so let's see what we got it. Oh, okay, go ahead.
So that dark region you see is actually a density change. There's a huge density jump before and after the shock. Okay, And when light travels through the air, it gets refracted differently. That's why this appears darker. Okay? So these are very real things, the shock waves. And the numerical methods we use have to be changed slightly to accommodate for that. Is this incompressible flow? Not incompressible flow. This is a huge change in density. So the material element changes its density by several times. Okay? So this is all we have discussed up until now deals with incompressible flow. Okay? The conservation of mass was specifically nabla dot u equals 0 only for incompressible conditions. Okay. But eventually we will do numerical methods which can handle these things also. Okay, why did I tell you that? Oh, right, shockwaves. So this is the first order. Okay, let's see what happens with the third order or the second order. Okay, let's see the second order solution. Okay. Now you see our diffusion is much less in the beginning, but as we start forming a sharp gradient, the diffusion picks up. Again, because all of this is related to the del 2 phi over del x squared, the second gradient. That becomes very large at this point. Okay, make sense? All right, so this actually is called the solution of the implicit Burger's equation. If you've heard of it, it's called the, so Burger's equation is, the guy's name was Burger. It's del u by del t plus u del u by del x equal mu del 2u over del x squared. Okay. So it's basically trying to mimic exactly what happens in the Navier-Stokes, but for a very simple 1D formulation. And back in the 50s and 60s, people were very happy with this equation because they thought they could understand what happens in a full 3D Navier-Stokes solution by using this as a simplified model. Turns out there's many things that this cannot emulate, but it actually is a very nice equation for testing your schemes. Okay, so it's a very nice model equation. For testing schemes. Testing numerical schemes. And when I say numerical scheme, it's, it just refers to the way you discretize your equation. Whether you use a first order, second order, Runge-Kutta, or something else. Okay? Any questions? No? Okay, so I actually want to show you something else. Do I have enough time? Maybe I will show you the details next time, but we can go take a look at the wave equation, how the wave equation behaves. For that, I have the links somewhere. Yeah, next time I'll tell you what an XT diagram means and how it's related to all this hyperbolic, parabolic, and the characteristic lines we've been talking about. So we can look at two more things. Okay. What we're looking at here is the solution of not the advection equation, but the wave equation. In the wave equation, information at each point travels both ways, in the positive direction and in the negative direction. It's called the D'Alembert solution. I will show you next time. So what happens is one peak basically splits into two peaks.
Not on the computer.
Oh, sorry. Thank you. So, yeah, this is basically a pulse, an initial pulse, and if that's the initial condition. And if you solve the wave equation with this initial condition, what will happen is the pulse separates into two pulses, and they spread in different directions. And when they hit the boundary, You can either get reflected or you can pass through. Okay, so what will happen is they get reflected, and when they get reflected, they change the sign. All of this you can show mathematically, analytically actually. Okay, they will come back, they will combine, and this is similar to what happens in water waves. If there was no dissipation in the water, okay, in particular. Okay, so, and if you, I found one very nice applet where you can actually, so yeah, I think it's meant for high school kids, but it's very, very nicely made. Okay, what happens here is we have this, we're holding this side and we can produce a disturbance. And the wave equation is being solved to show you how this disturbance travels along the string. If we say there's no damping, what will happen if I say no damping? Exactly, this disturbance will never stop. There's no energy dissipation. So if I create any disturbance, it will keep going forever. Let me not go forever, and if this end is fixed, right? So everything is getting reflected back. See, this will get reflected back, but with an opposite sign. What will happen if I make that a free end? So let me make that a free end, loose end. Okay. Then the things don't get reflected back with a negative sign, but with the same sign. And all of this is basically solving the wave equation. It's a very simple but beautiful example. That's how waves travel on a string. Okay, so I will tell you more about characteristics next time. Do you have any questions? Please do the project earlier than later because it might take some time. It's very easy, but if you're not familiar, it might take some time. And email me, come to office hours. Any help you need, I'm here. So just let me know. Okay. So if there's no more questions, we'll see each other next week. All right.
I'm just going to tap that's it. I do somewhere. You need them all?
Yep.
Yeah. Well, you can take these.
Okay,
And
I will
I'll look
scan
in my
them.
office for 10. If I don't have it in my office, I have it at home.
Okay.
But I'll bring it to you.
Okay. I will scan it and I will send
Okay.
Dropbox.
Okay. All right.
Thank you.
Yeah. Okay, I actually have a second copy of it. But I thought it was
So
at home in my
go
office.
and eat your lunch and then we can meet up.
The rest.
Can you?
Yeah,
What time?
it was gonna be.
Right.
One.
But
1:30.
1:30.
Okay. Well. Okay.
Okay, and I will ask that.
Yeah, absolutely.
I'll ask Ashwarya to be there as well. She's our other planner.
Okay. Okay.
I totally get
So we will meet you there. No.
Let me ask Ashwarya. Can we meet at 1:30 today? Yeah. No, meet. Okay, huh? Have you met before?
No.
All right.
Nice to meet you.
All right. So yeah, we can all
Okay.
at 1:30
Okay.
in the office, in the lab, 268.
268. Okay. I will find where it is.
Yeah.
Yeah. Gordon come. Did Gordon come?
No, not yet.